Hey everyone, Mr. Houck here. In today's video, we're going to be looking at components of vectors. By the end of this video, we should be able to find the horizontal and vertical components of a vector, convert vectors between component form and magnitude direction form, and use vectors to model and solve velocity problems in context. In the previous video, we saw that vectors were directed line segments that have both magnitude and direction. Today, we're going to talk about the components of vectors, the horizontal component and the vertical component. So if a vector v is represented in the coordinate plane with initial point p, x1, y1, and terminal point q, x2, y2, then it turns out that the vector is equal to x2 minus x1, comma, y2 minus y1. What this is essentially saying is that we are taking the terminal points, x2 and y2, and from them subtracting the initial points, x1, y1, to give us the vector. Now, looking at this image here, if we have, again, here's our initial point P, here's our terminal point Q, the horizontal component is x2 minus x1. And the vertical component, right here, is y2 minus y1. In three-dimensional space for a vector v with initial points x1, y1, z1, and terminal point x2, y2, z2, then we can still do the same thing where we take x2 minus x1 for the first coordinate, y2 minus y1 for the second component, z2 minus z1 for the third component. Now, direction is critical when finding horizontal and vertical components of a vector. A vector that starts at point P and ends at point Q will have a different direction than a vector that starts at point Q and ends at point P. So therefore, the components of a vector must always be found by subtracting the initial point from the terminal point. So we cannot change the order here. We cannot say x1 minus x2, y1 minus y2, z1 minus z2. It must be the terminal points, x2, y2, z2, then subtract from them the initial points. Okay? Let's see some examples of this, how this works. So here in our first example, we want to find the components. Notice this is a vector in two-dimensional space. I'm going to go ahead and label the initial and terminal points here. So if I go down here, it looks like this point is -4, -3, and this is going to be our x1, y1 because it's the initial point. The terminal point is 4, 4, and this is going to be x2, y2. So the horizontal component, we'll start with that first. The horizontal component is simply the horizontal component of the terminal point, which is 4, minus the horizontal component of the initial point, which is -4. So we'll do 4 minus -4, which equals 8. The vertical component is going to be y2, which is 4, minus y1, which is -3. So 4 minus -3, that would be +7. So these are our components. Here's the horizontal component. Here's the vertical component. The vector itself would be 8, 7. All right, let's try another example. Here's we want to find PQ, vector PQ, and this is going to be a vector in three-dimensional space because P is the point -9, -2, 1, Q is the point -6, -2, 7. And let's go ahead and label these points here. So we know it's vector PQ. We're starting with P. P is the initial point. We're ending with Q, the terminal point. So P is going to be x1, y1, z1, and Q is going to be x2, y2, z2. So if I want to find the components, well, we're going to take all the points from Q, the terminal point, and subtract from them the points from P, the initial point. So we're going to do x2 minus x1, which would be -6 minus -9. Well, -6 minus -9, that's -6 plus 9, which is +3. Then we're going to do y2 minus y1, which is -2 minus -2. Well, -2 minus -2, that's -2 plus 2, which would give us 0. And then we're going to do z2 minus z1, which would be 7 minus 1, which would give us 6. So these are the components. The vector in component form would be 3, 0, 6. Awesome. Let's try another one. So we want to give the vector in component form with initial point 2, -7, 0, and terminal point 1, -3, and -5. Again, this is going to be a vector in three-dimensional space. Let's go ahead and label our points here. So this point, initial point would be x1. Go back, get shape recognition off. x1, y1, z1. Terminal point x2, y2, z2. And then we'll go ahead and do the same business that we just got done doing, x2 minus x1 for the first component, which is 1 minus 2, which is -1. Then we'll have y2 minus y1, which is -3 minus -7. Don't forget the double negative. This would be 4 because it's really -3 plus 7. And then we have z2 minus z1, which is -5 minus 0, which is just -5. So our vector in component form would be -1, 4, and 5. Or sorry, -5. And notice when I'm saying in component form, once you find your components, these are the components here. Once you find your components, component form is where we have these pointy brackets that we talked about in the previous video that signify that we're working with a vector. All right, in our next example problem, let's grab a different color here. If the vector v equals 3, 7 and has an initial point 2, 4, then what is the terminal point? Well, the terminal point, again, is going to be x2, y2. That's the point we're looking for. And we already know the initial point, x1, y1, is 2, 4. And we know that the vector, the resultant vector, is 3, 7. So what we're going to have here is the terminal point minus the initial point. So we're going to have x2, whatever that is, minus x1, which is 2, should be giving us 3. Because we know we should be getting 3 from x2 minus x1. We also know that we should be getting, if we take y2 minus y1, and y1 in this case is 4, we should be getting 7, which is right here. So this is pretty easy to solve. Here we could just add 2 to both sides. We get that x2 is going to equal 5. Here we can just add 4 to both sides, and we get that y2 should equal 11. And that tells us that our terminal point is the point 5, 11. And if we wanted to, we could do a quick check just to make sure our work is correct. So if this is x2, this is y2. If we did x2 minus x1, well, 5 minus 2 would equal 3. Check. And then if we did y2 minus y1, 11 minus 4 equals 7. Check. Everything turns out good. All right, let's talk real briefly about position vectors. A position vector, or a vector in standard position, is a vector that has an initial point at the origin. Given a vector with initial point p, 0, 0, 0, and terminal point q, x, y, z, then the position vector is simply x, y, z. Let's consider these practice problems. Give the position vector for the point -52, 9. Well, again, this is a point out in two-dimensional space, -52 being the x-coordinate, 9 being the y-coordinate, and our initial point is going to be at 0, 0. So initial 0, 0, terminal is that point right there, -52, 9. So the position vector is pretty simple. It's just going to be -52, 9 in the pointy brackets. In our next example, a vector in standard position has components 1, 8. What is the initial point? What is the terminal point? Well, once again, this is a vector in standard position. Being in standard position automatically means that the initial point will be 0, 0 in this case. And since it has components 1, 8, that means that the terminal point is 1, 8. that's the only way that we're going to get a vector in standard position with components 1, 8. Okay, so those are our pieces right there. All right, so in the previous video, we learned about unit vectors. We know that a unit vector is a vector with magnitude equal to 1. Now, it turns out for any vector v that we can find a unit vector u in the same direction as v. This can be done by dividing the vector v with its magnitude. So let's try a couple examples here. We want to find the unit vector in the same direction as vector AB, where A is the point -2, 4, and B is the point 1, 5. So the first thing I want to do is I want to actually find the component form of the vector AB. So that's what I'm going to work on first. I'm going to find a component form of AB because we're just given the points A and B. Well, we know component form is x2 minus x1, comma, y2 minus y1. In this case, so here's x1, y1, here's x2, y2. I know that because A is coming first, B is coming second, so B is terminal, A is initial. So looking at the math there, that's going to be 1 minus -2, comma, 5 minus 4, which is 3, 1. Okay, so we have in component form the vector 3, 1. Now let's go ahead and find the magnitude of that vector 3, 1. So the magnitude of AB is going to be simply the square root of 3 squared plus 1 squared. Okay, well 3 squared is 9, 1 squared is 1, 9 plus 1 is going to give us 10, so we get the square root of 10. So that's the magnitude of vector AB. So to find our unit vector in the same direction as vector AB, so I'm going to call it vector u, that's going to be vector AB, which is 3, 1, divided by the magnitude of AB, which is the square root of 10. So what we can do is we're going to take each of the components and divide them by the square root of 10. This would give us 3 over square root of 10, comma, 1 over square root of 10. However, we know that we don't like square roots in the denominator, so let's go ahead and rationalize the denominator by multiplying the square root of 10 over 10 to both the numerator and denominator for both of these pieces, both of these components. And the result would be 3 square root of 10 over 10, comma, square root of 10 over 10. And let me make this look a little bit more like a pointy bracket. There we go. Okay, so again, the process there was get our vector in component form, which was 3, 1, find the magnitude of our vector, which was the square root of 10, take our vector, divide the components by the square root of 10, rationalize the denominator, and we had our result. Let's try another one. Find the unit vector in the same direction as the given vector. Notice that this time we have our director given in not component form, but we have the standard unit vectors I, j, and k, the linear combinations of I, j, and k. So we're going to do the same thing, though. We want to write our vector in component form, so I'm going to go ahead and call this vector v. So vector v equals negative 6i plus 2j minus k. And in component form, this would simply be -6 to -1. Let's go ahead and now find the magnitude of this vector v, as I'm calling it. So the magnitude of v would be the square root of the components squared and added together. So -6 squared plus 2 squared plus -1 squared. If you're using a calculator, make sure that you put these in parentheses. If you just do -6 squared without the parentheses, your calculator will calculate 6 squared, then apply the negative last, and you don't want to do that. But we would end up getting square root of, let's see, -6 times itself is 36. 2 squared would be 4. -1 times itself would be 1. And this would give us the square root of 41. Okay, so we have the magnitude of this vector is the square root of 41. Now what we're going to do to find the unit vector u, it's going to be the vector in component form, -6, 2, -1, divided by the magnitude, square root of 41. So we're going to take each of those components, divide them by the square root of 41. This would give us the vector -6 over square root of 41, 2 over the square root of 41, -1 over the square root of 41. Now, just like in the previous example, we don't like square roots in the denominator. Let's go ahead and rationalize the denominator for each component. This would give us -6 square root of 41 over 41. Then we would have 2 square root of 41 over 41. And lastly, we would have negative square root of 41 over 41. And this would be our unit vector u in the same direction as the vector that we started with. Okay, so those are two examples of how we can take any vector and find a unit vector in the same direction as that vector. Now let's look at a quick application of vectors, in this case velocity. And velocity is one of the many applications of vectors. The velocity of a moving object can be modeled by a vector whose direction is the direction of motion and whose magnitude is the speed. So in this example, a ball is thrown with an initial velocity of 70 feet per second with an angle of 35 degrees with the horizontal. That means that in this image right here, here's the ball being thrown at 70 feet per second. 35 degrees with the horizontal means our angle 35 degrees is right here. Okay, so we want to find the vertical and horizontal components of the velocity vector. Initially, we have this, what that means is, not initially, essentially, what that means is we have this velocity vector right here, 70 feet per second, and we want to find its horizontal component, which would be this velocity component, and we want to find the vertical component, which would be this component right here. Okay, so I'm going to go ahead and label this as, x for the horizontal component and y for the vertical component. So let's see, x horizontal component and y will be the vertical component. All right, so we're going to use some of the trig that we've already learned here in this course. I know that this is a right triangle. Y is opposite of the 35-degree angle, and 70 feet per second is acting as the hypotenuse, which means that I can take the sine of 35 degrees, so the sine of 35 degrees, and that will equal the opposite leg, y, which is one of the pieces I'm looking for, divided by the hypotenuse, which is the 70 feet per second. Multiplying 70 on each side, this means that y is equal to 70 times the sine of 35 degrees. And then I can go ahead and plug this into a calculator to calculate. Now just keep in mind, this problem is working in degrees. Make sure that your calculator is set to degrees, and this will give us that y is approximately 40.15 feet per second. And that is the vertical component, because we just solved for y. Now let's solve for the horizontal component. So if I want to solve for x, notice that relative to the 35-degree angle, x is the adjacent leg, and 70 is, of course, still the hypotenuse. So I could take the cosine of 35 degrees. That would be equal to the adjacent leg divided by the hypotenuse, x divided by 70, which would then mean that if I multiply 70 on both sides, x would equal 70 times the cosine of 35 degrees. Plugging this into a calculator and rounding to 2 decimal places, this would give us that the horizontal component is approximately 57.34 feet per second. Notice that the horizontal component and the vertical component are still both velocities. Okay, feet per second is our units. One is the horizontal component, one is the vertical component of the velocity vector.